Chapter 17 is going to review some thermodynamics concepts that we've already covered, and then it's going to go into more details about spontaneous reactions and entropy. And we'll talk about both of those in detail. So first of all, let me just clarify between kinetics and thermodynamics. Those are two different things in chemistry. Kinetics predicts how fast a reaction will happen, and the pathway is important. We talked about the collision model and how reactions proceed, but for thermodynamics, the pathway is not important. It's just the initial and the final amounts that we look at. And so thermo lets us predict whether a reaction will actually happen or not, but it doesn't tell us how fast it's going to happen. So we're going to go through the several laws of thermodynamics, and the first one says that energy cannot be created or destroyed, which is similar to the law of conservation of mass, and this basically just says that the energy of the universe is constant. So we can turn energy into different forms of energy. We can turn potential into kinetic, or kinetic back into potential, but we cannot completely destroy energy or just have less or more energy. So this word spontaneous, you need to be familiar with this word. Spontaneous means that the reaction will happen without any outside intervention. So what that means is that you don't have to heat it to make it continue to react, or you don't have to do anything to it. And a lot of students interpret that to mean that it happens quickly, or violently, explosive. And that's not what it means. It could. Some spontaneous reactions are violent and explosive, but not all of them. So there's an example there. It says combustion can happen quickly, but the conversion of diamond to graphite is extremely slow, but it happens without us having to do anything, and so it's still considered to be spontaneous. And there are two factors that you consider when you're looking at whether a reaction is spontaneous or not, and one of them is entropy. So entropy we've talked about before. The letter is S. This is a measure of the randomness or the disorder of the system. And the universe is going towards more disorder. So it's easier to make things more disordered than it is to make them ordered. And nature always chooses the lowest energy pathway possible. So it's kind of like with your bedroom. It's easier to have it be messy than it is to fold your clothes, put them in the drawer. It takes energy to make things ordered. And so nature, like I said, prefers less energy. So the driving force is that the universe is trying to increase the amount of energy. Entropy is a thermodynamic function describing the number of arrangements that are available to a system. So the more arrangements you have, the more entropy there's going to be. And that is why this is related to the number of particles. So this is the first one of the entropy changes. So the more particles you have, the more positions they can take, and that means that the entropy will increase. And when we talk about particles, we're talking about the coefficients. So if we had like 2A yields 3B, we just increased the number of particles. We also could talk about changes in states of matter. So gases have the most entropy and solids have the least. And we can talk about changes in temperature. So the higher the temperature, the more entropy there's going to be. Positional entropy is exactly what it sounds like. You hear the word position in there. So again, the more positions you can have, the higher the entropy is going to be. And notice what I have highlighted, that the increase and if you increase the volume of something, you increase the amount of positions that those particles can take, and that's going to increase the entropy as well. The second law of thermodynamics says that in any spontaneous process, there is always an increase in the entropy of the universe. So in other words, the entropy of the universe is increasing, the chaos or the disorder. And for a given change to be spontaneous, the universe entropy has to be positive. So when we talk about, there's three different things we can talk about. There's the universe, which is everything. There's the system, which is what we're studying. So it would be like the beaker of water or your reaction, your flask that has the chemicals in it. And then the surroundings are what is directly near that system. So we usually talk about the system and the surroundings together. When we add those together, we get the entropy of the universe. So I have a few notes here. You can see at 100 degrees, there's more entropy as water vapor, which is why water boils at 100 degrees. But vaporization is endothermic, and we've talked about before that endothermic reactions are not favored by nature. They have more activation energy. So you may be wondering, well, why does an endothermic reaction ever happen? Why does it even turn to water vapor? It shouldn't happen if it's endothermic. And the answer is because it creates so much more entropy that it outweighs the fact that it's an endothermic reaction. And a lot of this does depend on temperature. You'll see that the entropy and the temperature are related. So we're talking about the direction of heat flow. This is something different now. This is the other factor that will affect spontaneity. So entropy is one factor. If you increase the entropy a lot, it's likely to be spontaneous. And then the other factor you want to talk about is the heat flow. So we have H is the heat, S is the entropy. For S, more entropy is favored. And for H, exothermic is favored, so that's going to be a negative delta H. So this is what's favored in nature. And both of these factors are going to decide whether or not the reaction is spontaneous. So first of all, just remember that exothermic reactions means they're giving off energy from the system to the surroundings. Endothermic means that the surroundings are given energy to the system. And this is kind of important here that sometimes they talk about when you're transferring energy, what makes a bigger difference, a high temperature or low temperature. And I always think of this example that I have written down there. If you have $50 and you give it to a millionaire, then it's not a big deal. They don't really care about $50. But if you give it to a broke college student, they could probably eat off that for a month and have groceries for a month if they're careful. And so it makes a difference whether or not the temperature is high or low. So the lower the temperature, the lower the amount of money they had to begin with, the more little increments of money would affect them. And it's the same thing with temperature. So there's a few important things about the entropy of the surroundings. And the main one is that it depends a lot on temperature. So notice that when temperature is greater than 100 degrees above the boiling point, then the liquid water is going to turn into gas. That's going to be a spontaneous process, and it's endothermic. At temperatures less than 100 degrees, it's more spontaneous to go from gas to liquid. It's going to condense, and that's going to be exothermic. So it depends on the temperature. And we're going to incorporate those delta S and delta H's and the temperature into this equation that you're going to use quite often that equals Gibbs free energy. And this is a really important concept in chemistry and science in general, actually. So Gibbs free energy is going to relate the energy of the system to whether or not it's going to be spontaneous. And this equation that I have highlighted, it's in your reference packet, but it's one you're going to probably use on the AP exam at some point. And it says that the Gibbs free energy is equal to the delta H, which is the heat of the reaction, minus the temperature times the entropy. So if they give you the entropy amount and the heat amount, you can calculate, and the temperature, you can calculate the delta G. And we're going to talk about what delta G means in just a minute, but you can figure out whether it's spontaneous just from that. I do want to highlight a few things that will help you for your progress checks, though. The first thing is to be really careful and watch your units. Delta H is almost always in kilojoules, and delta S is almost always in joules, which is just confusing because then they don't match. So whenever you're given a list of data about the delta S or the delta H, make sure that they match either both kilojoules or both joules. It doesn't matter which one they are as long as they both match. Also, this little thing over here is super important. At the boiling point or the melting point, delta G is equal to 0, which means you can plug in 0 for delta G and rearrange the equation so that delta H is equal to T delta S. So many times students see questions where it says it's at the boiling point or the melting point, and it gives them 2 out of those 3 variables, like maybe delta H and T, or T and delta S, and asks what's the third one, and students try to plug it into that Gibbs free energy equation, and then they're like, wait, I'm missing a variable, I don't have enough information. So they expect that you know that at the boiling point and at the melting point, that the delta G is going to be equal to 0. Okay, so here's what delta G is going to tell you. So first of all, a negative delta G means that the reaction that's happening is creating less energy, which is what the nature is going towards. Remember, nature prefers the most stable arrangement of things. More stability means less energy. So that means the forward reaction is going to happen spontaneously. If it's a positive delta G, it means the backwards reaction is going to be spontaneous. And a delta G at 0 means that it's at equilibrium, so it's not shifting. So we can use this chart down here to figure out whether something's spontaneous or not, but you actually don't even need to use the chart. You can just figure it out yourself. So in terms of delta H, up here we said in the red up at the top, it says that negative delta H is favored. And we said that positive delta S is favored because more entropy and less energy would be preferable. And if you plug those into this equation, So if we have a negative delta H and we're subtracting a positive delta S, no matter what numbers you plug in for temperature, you're always going to end up with a negative value for delta G, and it's always going to be spontaneous because it's both things that nature is preferring. If we switch it and do the opposite, so if we have positive delta H, which is endothermic, and negative entropy, so we have more order, neither of those two things are things that nature is preferring, so that is going to give us a positive delta G value, and that means it will be non-spontaneous all the time. And again, you could test that. So if you plug in a positive value for delta H and a negative value for delta S, a negative, and when you subtract a negative, it makes it into a positive. So again, no matter what numbers you plug in, you're always going to get a positive. So that's going to be non-spontaneous. And then probably the hardest ones are if you have one that's favored and one that's not. So in the next example, negative delta H is favored, that's exothermic, but if you also have negative entropy, that means you're creating more order. What will happen? Well, it will be spontaneous, but only if you have low temperatures. So when you plug in the numbers, it will work out to give you a negative delta G if this whole factor is low enough. And then same thing if you have positive and positive. So endothermic is not preferred, but if you create a whole lot of disorder, it will be spontaneous if you have high enough temperatures. And this whole chart and the whole idea of delta G and that equation you're going to use quite often. So you'll use that in the progress check for today.